And I'd now like to invite to the stage Advenit, Makaya, an advanced manufacturing engineer at ISA, and also Jaroslaw, who is the general manager at Redwire Space Europe. Both of those have organized the next section, and they're going to take their place on the stage. And the next 4 speakers before lunch are all on site. So please welcome to the stage our first speaker, David Marsh. And David is going to talk about Nanoracks, space debris as a resource, promoting sustainability by repurposing launch vehicle upper stage. And this section is space to space. Thank you.
Hello, everyone. And thank you for the invitation to present today. My name is David Marsh. I am responsible for space station strategy in Nanoracks. What I'm going to be talking about today is how we can think about space debris differently. It doesn't just have to be debris. We can treat it as a resource. Before I talk about debris, I'd like to take a step back and talk about Nanoracks, who we are, how we got here, and what we're going to be doing in the future. So as you can see here, we've deployed over 1,300 payloads to the International Space Station. We've deployed, it's not listed here, but about 350 satellites and 11 million hours of space flight heritage for our components. We understand better than any other company the risks to the space environment caused by debris. Our customers use it every day, and our components are up there right now on the ISS. We've also worked with 35 nations around the world. Many of those are in Europe, and we have a European presence in Turin, Italy. You can also see here on the right a design of a future space station that we're currently working on with NASA. The Director General of ESA yesterday, Oshbacher, mentioned that there are 4 companies developing space stations. Nanoracks is one of them. So you see the design here. In 2027, when we complete this station, we will have billions of dollars worth of assets in the space environment that we need to protect. Therefore, we have a vested interest in figuring out ways that we can support solving the debris crisis. So let's talk about debris. I'm sure many of you have seen this chart around this conference. It's from the Space Environment Report that ESA released a few days ago. And of course, you can see that debris is a growing problem, right? Runaway Kessler syndrome, we've all heard of it. Specifically today, I'm going to talk about those colors in red, or the red and orange you see there. That's debris that's related to rocket upper stages and other parts of rockets. Now, to be clear, current efforts to remediate upper stage related debris are successful. As you can see in this chart also from the ESA report, the green bars represent successful attempts to remediate upper stage debris. That's done in 3 different ways. For more local, lower Earth orbits, the upper stage is burned up in the atmosphere. For more distant locations like GEO, GTO, the upper stages undergo a process called pacification and are placed in a graveyard orbit, typically a few hundred kilometers above the geobelt. And if it's a more distant launch, like for example the James Webb Space Telescope, that upper stage is launched into a heliocentric disposal orbit. So those 3 methods allow us to reduce the impact of upper stage debris, but they're not inherently sustainable. The debris is still up there, and it can still cause problems. You can see some news reports here on the right. Just a few months ago, an upper stage collided with the moon that was formerly in a heliocentric disposal orbit. We can't have that happening. You can see here another one. When you burn up upper stages, there can actually be challenges or problems caused to the ozone. For example, when aluminum is burned up in significantly large quantities, it becomes an aerosoled alumina, and that punches a hole in the ozone. If the space growth continues and there are hundreds of launches a year, this can be a growing problem, not to mention with massive super constellations. And finally, even when you burn things up in the atmosphere, it can cause problems. It can crash. And so all of these demonstrate that there's a better way of solving the upper stage debris crisis. What if there was a way that we didn't have to just reduce its impact, but we could actually reuse or recycle the upper stages themselves? You can see here a hypothetical rendering of an upper stage repurposed as a communications relay around the moon. We actually have funding from NASA and are currently working on a study to address the feasibility of this concept. Before I go further into our solution, I want to take you back a little bit and talk about the history of upper stage repurposing, because this is not a new idea. Very early on in the space age, in 1966, the US government actually used an upper stage for what they called the Agena target vehicle. So as a part of the Gemini program at NASA, they used this as an object to rendezvous with. So a human crewed spacecraft attempted to rendezvous with this many decades ago. Later, in 1973, the original concept for the Skylab workshop, the first United States space station, was actually going to be built using a formerly used Saturn upper stage. They ended up using a stage as kind of the outer structure, but there was never any fuel in it. But it demonstrates this was an idea that people were seriously considering. NASA was actually using these techniques. More recently, and perhaps a little bit more relevant to the discussions at this conference, NASA used an upper stage in 2009 to crash into the moon and to study the impact characteristics. That mission was called LCROSS, and it used a Centaur upper stage. So what's different about what we're doing? Well, there are a few things here, but we've designed a system that we call the Mission Extension Kit, or MEC. You can see it here at the top of the stage, mounted around the gold ESPA ring with the deployable solar arrays. And this allows us to control an upper stage after the primary mission is complete. We can generate our own power, handle our own communications and data handling, and we can point and maneuver the stage as necessary. That allows us to ensure that these upper stages don't become uncontrollable debris. Why is this possible now? What's different about our approach? First off, over the last few decades, there's been a significant miniaturization of technology. This is the CubeSat revolution that Nanoracks is extremely familiar with. Right? It's now possible to have commercially purchased components that are smaller and more capable than they ever have been. In order for this to work, we're taking up payload performance on a rocket, payload performance that a company is trying to sell to a payload customer. But we're taking up some of that volume to then get some other use out of the stage, so we need to minimize our mass as much as possible. Another factor, growing experience and comfort around the industry with rideshare payloads, secondary payloads. Transporter missions with SpaceX demonstrate how you can put 40-plus satellites on a single launch. SLS, the new space launch system from the United States, will actually have 13 hosted payloads and CubeSats on the Artemis 1 mission. We're comfortable putting secondary payloads on a multi-billion-dollar launch vehicle. Because of this, we need to be able to attach our system as a secondary payload and demonstrate that there's no risk to the primary payload, again, because of the investment that's made by that provider. Finally, there's a growing ecosystem approach to debris and to space as a whole. Whether this is government starting to recognize the issue posed by debris. We've seen ESA fund some demonstrations for active debris removal. JAXA has funded similar ones. The United States has actually started the first US government project to promote debris sustainability, a program through the Department of Defense called Orbital Prime. And there are hundreds of companies that are developing solutions. Nanoracks is one of them. You'll hear from a couple more after me that are all trying to work together to solve this problem. It wouldn't be possible if just one company was trying to solve it alone. We're also trying to solve recycling. Once we can control an upper stage with our mech, then we can start to do other more interesting things with it. Eventually in the future, we want to turn them into those communications relays for NASA, but another immediate project we're working on is recycling. And we're doing that through an experiment called Outpost Mars Demo 1, which will be launching in no earlier than 23 days, where we will actually be demonstrating a first-of-its-kind friction milling technique to cut through metal in space. Nothing has been done of this sort before, and we developed a solution to both prove the capability and host it in space as a hosted payload. So MARS stands for Multiple Accommodation Research System. That's the schematic you see on the right there. That allows us to provide our own power, data, everything we need to conduct this experiment totally independently of any other spacecraft. The actual kind of lighter gray color you see to the left of that schematic is the experiment itself. So that's a multiple level of containment box within which you see this picture here to the left, where there are 3 metal coupons. Each one is representative of the metal of an upper stage. And we're going to use that drill bit you see to the left. It's going to spin extremely fast. It's going to generate an extreme amount of heat where it first contacts the metal, and it's essentially going to heat up that metal and push it out of the way. Push it out of the way slow enough that it then re-solidifies once it gets shoved apart. And that allows us to cut through metal without creating debris fragments. If you're going to shave through metal when the whole spacecraft is traveling thousands of miles an hour, that becomes extremely dangerous metal fragments, and that's obviously the problem we're trying to solve. So we'll be flying this on a Transporter 5 rideshare mission. Like I said, Transporter 5, which is here in about 20 days, no earlier than. So I invite you all to stay tuned as we conduct this experiment. We're extremely excited for this, not only because it fits into the applications that we're working on for upper stages, but also because of its impacts across the solar system, things like manufacturing, lunar surface construction, right? If you want to build something, you need to be able to cut your feedstocks down to size and then weld them together. So we think this is a critical capability that could work with some of the other people that you'll hear from today to create and continue pushing forward that ecosystem approach. So what's next? Well, we're going to launch OMD1, and then we need to analyze it. We need to take a look at the results. We'll get some video, some thermal data, and we'll be able to understand if the technique is successful, how we can improve it. And because we're doing different cuts over those different coupons, we can modify it a little bit to get some useful data. Then we're going to do an OMD2, an Outpost Mars Demo 2. And this time we're going to focus on welding. There are a couple different methods we can use. Welding is a little bit more proven in the space environment. But we're going to analyze which technique works best with those friction milled cuts. We think that's important to show a combined approach. The mission extension kit, the mech that I addressed earlier, that will be launching in 2025 aboard a Centaur upper stage. That'll prove that we can actually control one of these stages and then implement some of these other techniques. And we're working to build partnerships in the United States and across the globe. So you can see some of them here. I feel like people always put in one slide with just a ton of logos of the companies they work with. I selected a couple ones here that we're working with to show a complete approach to recycling debris. There are a number of active debris removal companies, and we're working with everyone to understand how we can combine our technologies. There are a number of metal refining companies, who are also working on this that we're partnering with. And of course, Voyager Space, the logo at the top and the pin I'm wearing now is our parent company. But I would be remiss if I didn't speak about some of the challenges that the industry is facing today, specifically when it comes to repurposing debris. The first one, policy and regulatory questions. We're going to be salvaging, modifying an upper stage that's owned by another company or a government. And that can be very complicated, especially if we're trying to turn it into something else, offer a service with it, whatever it may be. And so there are questions there that need to be solved. And we're working with that ecosystem to find the right way of answering those questions. We also need to figure out how the ecosystem can continue its growth, right? Capital markets over the past few years have been extremely excited to invest in space. That cannot last forever. And so we need to understand a way that we can all collectively approach the coming situation. So to use an English idiom, a rising tide lifts all boats, that doesn't help you if your boat isn't in the water yet. And many startups are facing challenges raising capital and finding ways to test their components. And of course, Nanoracks is here to help you guys find ways to fly to space. Finally, we're seeing a growth, not finally, but next, we're seeing a growth in proliferated constellations, right? Project Kuiper just announced their 80-plus launch vehicles, or their 80-plus launches to develop their constellation. That's rocket stages that potentially will become more debris. If we don't find solutions to this challenge soon, then we're just going to perpetuate just kind of pushing them off to the side and worrying about it later, right? The way I characterize our current approach to upper stages is you push it into a landfill. You push it off a little bit where nobody is yet, and you figure out a way to deal with it later. We're trying to prove out the technologies to finally deal with the problem in a sustainable way. Finally, this is a little bit more of a positive note, reusable launch vehicles, right? If SpaceX is successful with Starship, then it'll be an incredibly beneficial thing for our industry, right? Decreasing launch costs is inherently good for most of us, unless you're another launch vehicle company. But there are still challenges there, right? Technically, regulatory, you can see a news article there that the FAA delayed their Starship test again.
Sorry, David, 1 minute.
Oh, thank you. So they delayed their FAA, the FAA delayed the report again. So while it's coming, it's not here yet. And so we need to start thinking about a solution. So that's all I have for you guys today. Thank you very much for the time. Happy to answer any questions.
Thank you, David. We have a bunch of questions for you, so maybe some of them you could answer later. We can see that your presentation brings a lot of attention. So first of all, thank you for joining us. It's great that Nanoracks is going beyond its traditional, I think, business model and joining to the space resources utilization. I will start from one, maybe first question from Sumit. Can upper stages be put in the lunar free return trajectory and then captured during rendezvous at LEO?
Absolutely. So of course this is an orbital dynamics question, but we've already seen upper stages be placed into lunar orbits. Eventually there will be launches to NRHO, near rectilinear halo orbit, where an upper stage could theoretically be placed, allowing it to come closer to the moon. And maybe there's a way that you can repurpose the fuel tanks of that upper stage itself and support that lunar fuel economy. So there are a number of possibilities here once you prove out the ability to actually capture and control the stage, and that's what we're trying to do with the mission extension kit.
Okay, thank you. I will pick up another one that is a little bit more legal, so probably legal people here will like it. What is incentive for owner of the debris, space object owner, to give away the ownership of the object to the debris recycling company?
Great question. And there's lots of different answers here, but the main thing is it depends on the launch vehicle, and it depends on the relationship, right? So there could be, if we're just going to repurpose it, or if we're going to use it for an additional service, it can be a revenue sharing model, it can be some sort of licensing model. There's a couple different ways we can approach it. If it's just salvaging it to then cut it up into a product and sell later, it could be as simple as just buying it like you would a decrepit old chip. Right, so there's a couple different approaches depending on whether you're going to just repurpose the structure or whether you're going to actually carve it up and use it for something else. But we're actively working with launch vehicle companies to solve these questions.
Perfect. Last one is from me. So where is, in terms of recycling, where is your commercial breaking point, where you see your first commercial application of recycling that clearly will generate for you a revenue, and it's no longer a tech demo, it might actually be a revenue stream?
Sure. So with that first mission extension kit in 2025, we will generate commercial revenue through hosted payloads. And so that'll show the repurposing concept is actually capable of being a sustainable business model. The recycling is a little bit further away, unfortunately. So while we'll be able to show this year that the actual cutting is possible and next year that welding is possible, combining those two is a little bit more difficult. And then adding in a third piece of actually providing something useful from it, whether it's for construction or some sort of other application, that's even further away. So I'd like to say that kind of this full debris recycling value chain could theoretically be possible in the next 6 to 8 years for sure, but that's going to require partnerships with a number of other companies.
Perfect. Thank you for your presentation.
Thank you very much.
Our next talk, also in here, which is great, on site, is Frank Koch, who's going to talk about turning waste into value from space debris to space resources.
Good. So one of the best things which could happen to a speaker is when the previous session more or less explains all the background of your own session, so you can save time and focus on other topics. So thanks a lot. So what is OrbitRecycling doing? At the end, we developed the concept of space debris recycling and found a business case behind it. If you look at the space industry today, mostly it's a linear economy, means we produce something, we use it, and then we throw it away. And that's not specific to space industry. There are a lot of industries doing the similar things. Now, everybody is aware that this is not really sustainable. So a circular economy is what we hope to approach one day, where we really use all of these resources. Unfortunately, that's not even the case on Earth, so why should it work in space? But in between, there's something which is pretty common to Earth. That's the recycling industry. And we presented that concept on the first Space Resources Week 3 years ago, I think 2019, in a poster session where we explained the business case behind it, where actually recycling brings you money, right? We are not depending on public funds, so we are more than happy to get them. There's a business case behind, and just for your information, the recycling industry of Germany alone has a bigger revenue than the whole European space industry. At the same time, it's also limited. So in Europe, we have roughly 3-4 companies who own the recycling market, which is pretty similar to space, right? So right now, OrbitRecycling is mainly a consultancy company. So we earn money by telling people that actually their space asset is quite good for their actual purpose, but there's a secondary life behind, means they could even earn money from recycling. So if you drill down a little bit, we start with this space resource, right? Some people call it waste or debris. It's actually a resource. And that resource can be reused. And we just saw the example of these upper stages. Now, there can be a lot of things be done out of upper stages. In our case, we just looked at the raw materials itself, because recycling of raw material is the most easiest process you can imagine. Electronic waste recycling doesn't even work on Earth. A lot of other things doesn't even work, but raw material recycling is really working, and it's very, very simple from a process point of view. Still complex, but very simple compared to all the other processes. So we focus on these raw materials, and then we're searching for an application of these raw materials, which is in space production. So how can you imagine that someone actually buy raw materials from you in a large amount of quantities, right? It's great that you produce maybe a very large antenna for specific satellites in space, right? Too large to be transported from Earth. But from a material point of view, that's still just few kilograms, and you have to launch a huge infrastructure to create these few kilograms, right? So the business case is a little bit problematic behind. But if you think about space stations, they require a very large shell to protect your astronauts, your robots, or whatever. So that might be an interesting use case, and that's what we focus on. We are more or less thinking about the Lunar ground station, which will be established sooner or later. And we want to be ready at that time to provide the necessary resources to help the construction of that. So for this, we need to transport these resources to the moon, and we just saw a nice presentation where technology is actually developed from industry players to support us here to bring these resources from GTO further to the moon. From an energy perspective, that's quite interesting. Roughly 75% of that energy was already spent by launching it into GTO, so we can even use very small propulsion technology to do this. When we are closer to the moon, we developed the concept of a soft landing zone where we more or less transport it down to the lunar surface in a way that more or less these resources will disassemble themselves in smaller fragments, which we will store in our depository on the lunar surface until we actually can repurpose them. For the recovery and transportation from our depository to our refinery stations, we depend again on industry players to help us here. While we develop an own rover concept to do so, there are so many companies out there who have very great skills, and you see even them here in the exhibition area, that we probably more or less cancel our own rover development and work with these companies to do so. Worst case is we still use our own rovers. But our main competency is really the resource recycling and processing of the raw materials. That's what we presented last year at the Space Resource Conference. We really are able to cast aluminum from space debris in regolith molds. So we use the moon dust to create mold, and then we melt the aluminum from space debris and cast new objects out of it. In the session this morning, I showed these wall segments, which are here also on the pictures. We also cast tools, very simple way, but that's more or less the easy approach for casting, right? Rough structures, wall segments, very large, very easy to produce, like 4 by 3 meters, and we can create like a containerized moon station. Tools, you simply press your broken tool in the moon dust, you heat up the aluminum, you do the cast, and then you have a replacement tool, much faster than out of a 3D printer. But what if you're really looking for fine structures? What I have here in my hands, and I am happy to show it later to you when you approach me, That is a small rod with a tiny hole in it, which can be used for a thruster. So there are vacuum arc thrusters which run on solid metal. You just saw the flashing lights. These are the impulses from these thrusters, in this case from Neumann Space from Australia. And we wanted to find out if you can repurpose these material from space debris, these are Ariane 5 upper stage material, to create such rods for these thrusters. So we can run our space missions directly on aluminium from our space debris. As you see on this picture, we do the cast, but still we have some post-processing to bring it in the required form, in the required shape. So we are wondering if this cannot be done better. And this could be done better after we approached a company from Berlin, Tivari, who is capable to 3D print regolith with some polymers together to create very fine structures. So in this case, we can create the required fine molds for our cast to create these directly. This is what we are currently trying to investigate, how we do this in the best way to create these molds to power our own space tugs with space debris to bring these upper stages to the moon. This is our current research, and that's what we're currently focusing on. But I didn't want to stop my presentation without showing one more thing we are also doing. And people who know me know I work for Microsoft, and for years I was waiting for this effect of these opening cinema slides. So what we are actually doing is we are bringing the moon down to Earth. Means I was able to get a huge hangar from an old airport to establish my own regolith testbed. So this is just a small animation how it will actually look like. So we will fill up that old hangar, this old terminal, with a huge regolith environment, mainly to test our own rovers. But I also figured out that I'm not using it 365 days a year. So we make this area public to anybody who's interested in doing their own tests in a regular testbed. Right now, it will be around 150 square meters. There will be a separate slope area. People approached me already that they also would love to have a drilling area so they can drill down 3 or maybe 2 meters to do these drilling tests. We will have full spectrum LED lights to simulate the lighting condition at the lunar south pole probably. We want to also implement a gravity assist so that these rovers are more or less have the same challenges as on the moon itself. And as I said, it will be completely open to industry, research institutes, or even private activities. So there's no need to fill out a large form, write 10 papers to justify why you want to use that environment. You will simply go to a calendar web page, and if it's free, you just can show up and do your tests. That's what we want to do there. If this sounds interesting to you, please reach out to me. Right now, we are defining the second extension of this. It's pretty easy to remember, just the moon at OrbitRecycling.space or the moon at PTS.space, because we operate this together with PTS, the company from Berlin as well. And I hope this is interesting for a lot of people of you, so we utilize this as much as possible. With this, that's the short overview after the nice introduction from my session before. And if there are any questions, I'm more than happy to answer them.
Thank you. Thank you very much, Frank. Very nice talk and good to have you here. We have a couple of questions from the chat. The first one is, why do you need to soft land the debris on the moon? Why don't you just, let's say, crash on the surface, use a solar concentrator to melt in the metal in the crater that you will have formed, and then retrieve the metal? So that's a question from Davide Mencio.
Actually, that's what we do. But the term crashing doesn't sound so nice, then dedicated landing concept which brings your debris in smaller fragments.
Understood. And we have a second question, is how do you plan to implement gravity assist in the lunar simulant environment from Sumit?
I use anti-gravity to, anti-material to simulate it. No, it will be a simply crane installation. So your rovers will hang on ropes, and then that limits the weight of the wheels in the regolith.
Understood. That's a common practice. And to finish, one final question from me about the processes that you selected. How did you come up with casting, and do you intend to complement this process with other manufacturing processes?
Yeah. So why casting? At the end, we really took a look at these space debris, right? We really analyzed this very nice database from ESA and others of these 40,000 objects, and we tried to find a business case for it. And as I said, raw materials this was more or less the only one which is very easy to implement. And when you then look at the materials used, you end up that aluminium is the most commonly used material in. So what do you do with aluminium? Well, you do aluminium casting. And casting requires a mold. So to avoid mold materials on the moon, we just tested casting in regolith, and it works perfectly. So it could be even done with concentrated sunlight, to pick up that question before. So we don't need a lot of additional energy. We use concentrated sunlight to create the molds, but also to melt the aluminium. Yes, electric furnaces are maybe even better to melt it, but it requires batteries, or it requires the furnace, while concentrated sunlights only need lenses.
Thank you very much, Frank. Thank you, Lisa.
My pleasure.
I like that, the opposite of crashing, or the equal of crashing, dedicated landing concept. I'm just going to save that in case I ever need it for insurance purposes. Next, our final talk before lunch is Joost van Oorschot, who is from Maana Electric, of course, and his talk is entitled Current Developments and the Roadmap to Producing ISRU Solar Panels on the Moon. Joost.
Yes, so maybe some of you already know me. I've been presenting at the Space Resources Week for some years now, and it's great to see that we have people always returning and also more people joining. So yes, I'm just going to talk a little bit about what we do at Maana and the progress that we've made in the last years or so, and also where we are heading more long term. So maybe just to start, for the people who do not know what Maana is, so we were founded in 2018. We have about 40 employees over 3 locations, and we consider ourselves a world leader in ISRU technologies. Especially what we are specialized in is space technologies, sustainability technologies, and power system technologies, and how ISRU applies to these fields. And really what we are very good at is everything from TRL1 to TRL6, and doing that very rapidly, I would say. So Maana itself, our master plan is quite simple. What we first want to do is build inexpensive solar capacity in deserts here on Earth. Then we want to build the same solar capacity on the moon, and eventually in the rest of the solar system. You know, sometimes you have to make it as simple as 3 steps, but there's of course some steps in between. So our main focus today is, of course, step 1, which is to produce our TerraBox system, which is able to turn desert sand into solar panels here on Earth. And that's what we've been working on primarily for the last 4 years. And just to give you an idea how that in its principle works, is so we take the sand and we purify this sand to take out the specific minerals that we need for our processes. So we produce silicon, we produce glass, all of these things for our solar panels. So we have to extract the silicon from the sand, specifically from the silica. We produce the glass from a mixture of different minerals, and then we turn this silicon into solar cells, which then, together with the glass, get turned into fully functional solar panels, which come out of our box. And this is a very gross simplification of how it actually works, but at least it gives you the idea. So here, just to give you an idea of where we are today with doing this. So we have been able to basically purify the desert sand to high purity silicon dioxide, so, or silica, quartz, whatever you want to call it, of about 98% and upwards, which is quite high purity. And this is quite revolutionary for producing high purity silicon, because if you know how it's done today, you usually go to a mine that already has 99% purity silica, and you extract it directly there. You don't take it from desert sand that has a relative low purity of 50, 60%. And besides that, we also are able to extract other minerals in the sand and combine that in order to produce glass. So we've been able to produce metallurgical grade silicon of about more than 99% purity, usually somewhere between 99.5 and 99.9% purity. And then we turn that into solar grade purity silicon. So I have a block here of what that looks like. And I have samples of all of these process steps. So if you are interested, you can come and see them later. So we've also been able to produce glass with optical transparency above 75% using only the desert sand. And we've been able to then turn the silicon that we have extracted from the sand into fully functional solar cells. So today we have about 12% efficiency on our solar cells, which is lower than the industry today on Earth does, but it's a good step in the right direction. We expect we'll be able to get to the 22% and higher that the industry is also able to do. And combining the glass and the solar cells, we are able to produce fully functional solar panels. So we're about 6 months away from having our first TerraBox system ready. And just to give you an idea, the TerraBox, while it looks very pretty on the picture of one container with a lot of robots, it's actually 6 shipping containers that work together with all kinds of processes inside to produce the fully functional solar panels. And we plan to test this next year in the desert. We have several locations around the world where we want to do that. So that will be the first demonstration of A to Z of ISRU technologies, of producing a complex product like solar panels from a raw feedstock like sand. And of course, we are doing this also for lunar applications. That's always been our vision and our dream. So we are working now on what we call step 2, which is our lunar production. So that's our Luna box, as we call it. And the Luna box, it's the same as the Terra box. We produce 1 megawatt of solar capacity a year. We target a lifetime of about 10 years. And we actually have as a byproduct that we produce oxygen when we are producing the materials that we need. And the Terra box in itself will be fully automated. And we want to, of course, do the same for the Luna box. And we hope to launch our first Luna box before the end of the decade, which would be a fantastic achievement, and I hope we can make it. So just to give you an idea, because it's a long road ahead to get there, really what we're doing now for the Luna box is first de-risking and validating some of the critical technologies in the process chain. And we're doing this using the Terra box. So about 60% of the technologies that we use in the Terra box translate quite directly to the Luna box applications. We, of course, have to do some modifications. It's a different environment, but it does get us there. And secondly, we're developing small-scale payloads of some critical processes to test these on the moon, because, of course, we want to make sure that what we are doing for Earth also will work on the moon. As a third step, we're also developing the ancillary technologies because, okay, it's great if you can produce solar panels, but you still need to interconnect those solar panels. You still need to be able to connect those solar panels to the customer, whether it's rovers, whether it's other landers. So we're also working on that. And we've also now set up our we are setting up our testing facility. So we have a dedicated Regolith lab, anechoic chamber, vibration table, TVAC, dirty thermal vac, all so that we can very rapidly develop the technologies that we want to eventually apply on the moon. And finally, what we are starting at the end of this year is the real design of the Luna box, so to say, to make it ready for the moon. So I think what's most relevant for this conference is probably Source, and some of you may have already seen it. Basically, the purpose of Source is to have in about 10 kilos a payload that's able to produce from raw regolith metallurgical grade silicon and produce oxygen. And you know, it's designed for a 14-day Earth life, so 1 lunar day. and really to showcase that the technologies that we are using here on Earth also will work on the moon. So we're quite advanced on some of these processes. I would say the regolith processing unit, so taking the raw regolith and basically extracting the right granulometry and so forth, is at about TRL5. The beneficiation unit, which we find one of the more critical components, is actually at TRL5 right now. And then the regolith reduction unit, where we actually produce the silicon, is also at around TRL4. And we're still identifying an analytical unit for the system. So I just want to talk briefly about our regolith beneficiation unit. I know there's a lot of people talking at this conference to neglect beneficiation, but I am actually a big advocate of beneficiation, because if you look at what we have a very, very small payload. It's about 80 grams that it weighs. It's about in a matchbox. It's very small. It uses relatively little power, and we can process almost 3.5 kilos of regolith and have separate streams of different minerals from that. And if you're interested to learn more, we can talk about it later. But it's very relevant. So if you are trying to do any kinds of extraction on the moon, having a beneficiation unit probably can reduce your mass and your power requirements quite drastically. So we're also open to partnering with other companies or institutions that are looking to get payloads to the moon to produce oxygen, to produce metals, and apply just one of our technologies or multiple of our technologies to what you are doing. And besides that, one thing that we found, because we have quite a lot of regolith simulants at Maana, I think at least 40, is that there's no real good regolith simulant out there, and probably a lot of you have found the same. And it really depends on your application case. So we've actually decided that we want to start developing our own regolith simulant. We want to actually also sell this, so we want to make it as easy for you to get our regolith simulant as it is to buy something on Amazon. We literally want to make it available on Amazon for you to buy a regolith simulant. And right now, what we've found is that there's, different fidelities of regolith simulant. You have the basic fidelity, which is really just rocks crushed up, and then you have a standard fidelity, which is what we're targeting, where you actually have a mineral composition which is okay-ish, and then you can go into the high fidelity where you actually get very close to what it could look like on the moon, but obviously cost increases drastically as you get to a higher fidelity. So we're really doing this for our own purposes, but of course always happy to share our simulants when possible. Yes, and so I talked about ancillaries before for making sure that we can actually provide power to future lander systems, to future rover systems. So we have this plug and socket that we've developed, and we have many other projects. We also have an energy storage project that we have ongoing, also how to make grid cables and so forth. Because it's just producing solar panels is not enough. It's important that we can also interconnect everything. And what I would really like is that we don't end up on the moon needing to exchange between a European plug and a US plug and the way that you have to do here on Earth. So we also want to collaborate with other companies on this. We are willing to offer, to an extent, our designs open source so that everyone starts using the same plug interfaces for the lunar environment, because really it's not worth us wasting mass on converting from one plug system to another. And yeah, that's just one of the many projects that we have going on. Next year I'll share way more when we have more advances on some of the other projects. So I just wanted to say thank you all for your time. And if you are interested in some of the tech, you can, of course, always contact us. I will be around with samples. So really from the full process chain, all the way from the sand or regolith, all the way to the solar cells, I have it with me so I can show you. And of course, I'll shamelessly also advertise that we are hiring. So if you are interested to do more, you are always welcome at Maana.
Thank you, Joost. As every year, it's a very cool tech.
Thank you.
And it's reflected by number of questions we have for you. It's around a dozen. So if you may stay here a little bit after.
Yeah, no problem.
But I will pick one. It's how much energy do you need to produce one package of solar panels And I think it's about terrestrial, and I will add a question. What your estimations, how much it would take to produce, I would say, lunar solar panels?
Yeah, no, it's a very good question, something that we look at constantly. And so on Earth, it takes us about 6 months to have produced enough solar panels to offset the amount of energy it takes to produce the solar panels. So the initial system, we do plan to grid connect it, but at some point, we could imagine where you could have it completely independent. And that's just because we want to start with full-scale production from the get-go. For our lunar system, really what we have in mind is to use a ramp-up on the production process. The same as you would throttle your engine in your car, we want to throttle our process. So maybe initially, the first lunar day, we might only produce a small 5% of our full production capacity using less power. And then as we produce more solar panels and we are connected to more solar panels, we can ramp up our production, so to say. So that's really our philosophy. Look, all of these processes are energy intensive. There's no way around it. And I think if you look at all of the presentations that have been here, everyone is always talking about power, and especially the power to mass ratio is important there. So we're just trying to offer an alternative, because you are going to need megawatt scale power if you want to do anything really useful on the moon.
Thank you. So I have last question from myself, since we are going to not for launch, but for lunch. I know that you are on in the period of fundraising right now. And we have a number of investors here, angel investors, that are not exposing themselves, but they are here. So why someone should invest in Maana Electric? What's your pitch to investors at the time of Tesla and cryptocurrencies? What's your pitch to investors?
I think the important thing, what we do at Maana, is that we do have that terrestrial business case, and we also have the long-term vision. So there's many companies out there that have a short-term vision, one product. We definitely don't have that. We have the long-term vision, but we also have a short-term to market. We're 4 years old, and next year we're commercializing. And that's important, because when you're looking at asteroid mining, it's going to take you 10, 20 or more years, and it's very difficult to get there, and you're going to need a lot of investment. So investors that are investing now, the big benefit that you have is that you're already close to commercialization with the technology that can disrupt the terrestrial market. For the terrestrial market, we offer a cheaper alternative to Chinese solar panels. We offer a cleaner alternative, so there's no CO2 production, there's no chemicals used in our processes. And finally, local production. And actually, the local production is the most important we see, because you know how it is now with the supply chains. The situation in the Ukraine has disrupted a lot of things. Also, the COVID situation has disrupted a lot. So being able to produce solar panels locally with very little feedstock material and quite versatile different feedstock materials, that's really an important technology to have in your arsenal. Yeah.
Perfect. Thank you very much.
Thank you, JJ.
It's amazing to see what he's done in 4 years, and he's really moved in parallel to Space Resources Week, which is the 4th edition at the moment. Yes, not launch, but lunch. That is next, and we'll come back here at 2:15, where we're going to talk about all of the legal aspects of space resources, and we will also be talking about investment. Thank you. Enjoy your lunch. Bon appetit. And back here in your seats at 2:15.